Hello everyone. Um, Today I want to talk about this paper briefly. This paper is on my list since it was released last month, but I didn't have opportunity to focus on that. And finally, today I have some time and I want to talk about that. Hi, it is Necati, a computer scientist with 20 years of experience, and I share my experiences and thoughts on this channel. Let's start. So let's start with some numbers, okay? This is a code world model. This model from Meta is an open weights LLM. The weights are open. It is 32 billion parameters, dense decoder only, and 131 token context size. So now here's the exciting part. What is the goal of this new research? The goal is to incorporating the world models for code understanding. So you may say, what do you mean code understanding? Like, don't we have right now cloud code, codecs, cursor? So that may confuse you, but let's talk about this. So currently, our traditional large language models are focused on syntax. What does it mean? It means the code is just text for them, okay? So they are trying to produce the code with the correct syntax, but they don't know what happens. The LLM itself don't know what happens when the code is executed. So, of course, with the help of agentic systems, now we are doing better, but at the end, fundamentally, large language models do not understand what is going on and what will happen when the code is executed. Now, with this model, we are trying to understand what happens, the semantics, what happens when the code is executed, how the execution changes the local variable states. Think about this. You have variables in a function, you are executing the code, there's a loop, and then each time there's a variable is changing, and now this is trying to understand that. And of course, it is also trying to figure out how the code changes. How a change in the code impacts the output of the program. So how it is done? It is done by doing teaching this process in the large language model training process. Let's talk about this. So basically, we have, as usual, like this general pre-training, and then this model, this research paper is introducing something called world model mid-training. That is the key innovation part in this paper. So it is not only trained in the code text, it is also trained on the sequences of action taken and the resulted state, okay? So you basically, the code is fed into LLM. Also, when it is executed, what is changing in the state, that is also fed into the LLMs. That is the main difference. So observation action trajectories, that is what I mentioned. Of course, also Python execution traces is fed into LLM. Line by line, what changes, how it changes. And also, at some point, they are providing some kind of agentic instructions to the large language model. So they are providing an environment, and so LLM interacts and then tries to fix bugs. And each time it takes action, it also observes the results and then is trained based on that. And then the regular post-training phase. But the key innovation is this phase. We are no more, this paper is no more just training the code as a text, but it is trying to train the code and the state pairs. This is the main key innovation. So if we have this, what are our capabilities, right? I mean, so of course, as I mentioned, now we have execution. Since we trained the system with input and output pairs, which means now it can simulate what is going to happen. So this is very important. Now you've give a code and it simulates what happens if it is executed before it is being executed. And they call it neural debugger in the paper. Of course, this is the ground reasoning part, execution prediction integrated with natural language. That's what we have. And agentic coding capability also is, as a result, is embedded in this large language model, generating solution, creating tests, comparing execution results. But the main part that I want to emphasize, underline, is step-by-step execution simulation. Now, when it generates the code, it is not only generating, it is understanding, it is simulating what happens when this code is executed. So this means faster bug solving, faster software development, and more bug-free applications. And these are the benchmark performances that you can also find in the paper. So, and I also wanted to take a look at the conclusion section of the paper, like what is it talking about. And basically they say, their vision is to bridge the gap between language level reasoning and executable semantics. And that makes sense because that is the goal. They are not focused on syntax, they are focused on semantics, they are focused on understanding. And when I look at the also conclusion, I am trying to figure out like what is the next step this paper can go. And they mention a couple of points. They mentioned this, we can do zero-shot planning with code vault models, grounded chain of thought reasoning, that's what they are talking about, and also reinforcement learning with sparse verify rewards. This can be another extension in the future. So we will see, I don't know. As I mentioned, model weights are released, everything is there, but they are of course saying this is a research model only, and it is non-commercial, of course. So that is it. I am excited about this paper, and I believe if the research goes in more and the tools, if we start seeing a tool ecosystem around this idea, I think we will start building faster and faster and bug-free applications. See you.